So we're very happy to have Arnab Priya Saha to tell us about the one loop integrand from generalized scattering equations. Over to you, Arnab.
Okay, first of all, I'd like to thank Professor Shiraz Miniwala and all other organizers of this quantum spacetime seminar series for giving me a wonderful opportunity to present our work here. So today I'll talk about one loop integrand from generalized scattering equations, and this talk is based on mainly this work done with Muhammad Abhishek and Subramania Hegre at HRI, and also partly based on our previous work done with Professor Dilip Jatkar. So let me begin by giving an introduction and motivation behind our work. CHY, or Kachazo-Haywan formalism, as we know it, is one of the remarkable developments in S-matrix program. It was developed almost a decade back, and since then it has sort of revolutionized our understanding of quantum field theory. And using this formalism, several quantum field theory amplitudes can be computed using integral representations over moduli space of punctured Riemann spheres. There are several novel aspects of this formalism. It is applicable to a large variety of non-supersymmetric theories, including scalars, gluons, and gravitons. It replaces the conventional technique of finding scattering amplitude by computing large number of Feynman diagrams, which is often laborious and complicated process. Several important properties of S-matrix like color kinematic duality, double copy relations, etc., are manifested easily, which otherwise are inconspicuous in the usual Lagrangian formulation. Studies of factorization properties of S-matrix under soft limits, collinear limits, etc., can be done very efficiently using this CHY formalism. And most importantly, it hints at alternative description of scattering amplitudes without the conventional Lagrangian formulation, and therefore it offers new insight to our understanding of quantum field theory. And although it was initially developed for tree-level S-matrix containing massless fields, but later there have been subsequent developments for to accommodate loop corrections as well as massive fields. Scattering equations are a very important part of this CHY formalism. They map kinematic space of Mandelbrot invariance to an auxiliary space, and in this case, auxiliary space is this moduli space of punctured Riemann spheres. And recently, Kachazo, Early, Guevara, Misera, CEGF, they introduced generalization of the scattering equations, which are now defined on higher dimensional projective spaces CP k-1 for k greater than 2, and k equal to 2 reduces to the original CHY formalism. Now, standard scattering equations defined on the space of n points on CP1 can also be thought of as scattering equations for n points on CPn-3. And this gives a nice motivation for studying generalization on higher dimensional projective spaces. For example, for n equal to 5, the scattering equations on CP1 are same as scattering equations on CP2. A well-studied example, and so far the only known one with this generalization, is so-called bi-adjoint scalar amplitudes. However, the physical interpretations of these amplitudes remain obscure, and in this work we focus on understanding some physical aspects of these scattering amplitudes. So these amplitudes have realizations in terms of Grassmannian cluster algebra, and in this work, using the Grassmannian GR36 cluster algebra, we relate the singularities of k equal to 3, n equal to 6 amplitude to 4.1 loop integrand in the bi-adjoint cubic scalar theory through the D4 cluster polytope. All these things we will explain in more details as we go along. And k equal to 3, n equal to 6 is the first non-trivial example of these amplitudes. And
sorry to interrupt you, Arnab. I already lost you. What is k? N, I suppose, pertains to CPn-3.
Yeah. So and k refers to the CPk-1. So this k.
Let me understand. So yeah, can you just explain that? So you have two CPs, and what is the relation then? Sorry, just one.
Yes. So for example, the original CHI formalism was CP1, scattering equations on CP1. So for that, k equal to 2. And now we'll study generalizations to higher k, for k greater than 2. Say, for example, we will consider moduli space of punctured CP3.
Okay.
Or CP2. So in that case, for CP2, k will be 3. For CP3, k will be 4, and so on. So in this case, we study n equal to 6, so 6-point amplitude on CP.
Okay. Sorry. N there refers to the n point.
Number of external states.
Okay, and k is the CPk-1. Huh?
Yes.
Okay, so you are going to look at CP2 and a 6-point amplitude. There.
Yes.
I see.
Yeah.
And that's the sort of first case where where you can investigate this map, is it?
For example, as we will see, for example, k equal to 3, n equal to 5 is related to the usual k equal to 2, n equal to 5. And k equal to 2 is the original CHI on CP1 for 5 point. And because of this duality that I just alluded here, so CP1, for n equal to 5, the scattering equations on CP1 will be related to n equal to 5 scattering equations on CP2. So there we already know the answer. So the first non-trivial case appears for n equal to 6.
Got it. Thank you.
Thank you.
And Arnab, one sort of context question. Roughly speaking, I had thought that CP1 arises in the usual CHY, that CP1 arises because it's like a sphere.
Yes.
And a sphere is natural for studying tree-level diagrams in string theory. Now, perhaps this was, but now you're looking at these higher dimensional surfaces. So it doesn't look like any string world sheet at all.
Yeah, a priori, there's no connection with string theory.
Yeah, so does this suggest that this similarity with string world sheets in the original Cachasso kind of construction was just a coincidence? So,
yeah, I mean, I'm not right at this point. I'm not able to answer this question fully, but what we can see and what we have also studied by going to various boundaries of these moduli spaces of high dimensional the CPK minus 1, we get back the k equal to 2 moduli space. So in that way, and if k equal to 2 moduli spaces related to string world sheet, so at various boundaries of these high dimensional projective spaces, moduli space of punctured high dimensional projective spaces, we get back some k equal to 2, the usual string world sheet kind of thing.
Yeah, and perhaps I could ask, is there some advantage of going in a situation which can be handled with CP1? Is there some advantage to going to CP2? Does something become clearer?
Yeah, so here what we study is that particularly for this example, k equal to 3, n equal to 6, we get one loop amplitude. And what Cachasso, Hay and Yuan, they did for k equal to 2, they got this tree-level amplitude, although there is a way of taking forward limit and going to particular loop amplitudes. But here, this is related to one loop 4-point cubic amplitude.
I see. So going to higher loop, in going to higher loops, there's advantages to going to higher k. Is this right?
That is not immediately clear. I mean, we have studied only particular case. So what happens for general k and general n, that is not yet known.
Okay, thank you. Sorry for interrupting.
No, thank you very much.
Sorry, Arnab. Hopefully, you will review this, right? I mean, where is this complex projective space coming from to begin with, and the Grassmannian, etc. are coming from?
Yes. So that I will.
A little bit.
Yes. Okay. So this is the outline of my talk. So first, I will give a lightning review of CHY. Then I'll talk about the construction CEGM, and then I'll talk about tropical Grassmannian, and finally, I'll come to our work, one loop amplitude, and talk about some factorization properties. Before ending with some remarks. So so let me start with this CHY review. So scattering amplitudes are expressed in terms of Mandelstam variables SAB, and these Mandelstam variables form a kinematic space, and typically dimension of this kinematic space is n into n minus 3 by 2, which is also equal to the number of independent Mandelstam variables that we can have. And the essential idea of CHY was to map the kinematic space to the moduli space of all n punctured Riemann spheres by this holomorphic mapping, where the sigma j's represent the external states of the scattering, which have complex momenta kj, and therefore these are maps of Riemann sphere into complex momentum space. And then imposing momentum conservation using that.
Sorry. Yes. Sorry. This number of the dimension of the modular space of Mandelstam variables, you said n minus 3 by 2, but it also depends on the dimension.
Yes.
You are assuming that you are in large dimension.
High dimension. Yes.
Okay.
So that Gram determinant conditions we can ignore for that moment.
Okay.
So, and what was Kj, please?
Kj are the momenta of the external states of the scattering process.
Yeah.
I see. So then you're working with the momenta themselves and not the Mandelstam variables?
I mean, yeah. So this is a map, and then when you dot with another thing, so ki dot kj, we can use them as Sij because we are dealing with massless particles.
Okay, thank you.
And Arnab, Sorry, I know nothing about the subject. Please forgive me. But when you started saying the first slide, I also thought, like Shiraz was mentioning, that perhaps the CP1 case is arising because of some massless limit of string theory. But okay, it seems more general. But at least for the CP1 case, roughly, can you relate this way of mapping amplitudes to the Riemann sphere with how we would relate, say, graviton scattering or something in string theory by introducing vertex operators?
Yes, I mean, there are close connections to that. And I think their original motivation, CHY's original motivation of finding quantum field theory amplitudes in this way, I mean, it came from the string theory. And the way we do this moduli space integration, that looks like introducing these, inserting the vertex operators and finding amplitudes in string theory.
I see. Okay. Thank you. Thank you.
Thank you.
Sorry, one more question.
Yes.
This Kj is a vector, right?
Kj, yeah, it's a vector, but I mean, we are considering every component. Yes. Yeah, Kj is a vector. Right. Kj is a d-dimensional vector.
So this P function P is also a vector.
I mean, yes, this holomorphic mapping is a vector. Basically, we take a dot product with another P, and then find the residue over the sigma, so that will have simple poles. So in principle, it is a vector. Yes. Yeah, but I'll not go to all these details. So what I'd say that I mean, imposing momentum conservation, we can arrive at a set of these n equations. So these are called scattering equations, and they play a very central role in this formalism. There are n such equations for every a, and this reads as summation over b not equal to a SAB by sigma a minus sigma b. And here these SABs are the Mandelstam variables that we get by dotting Ka with Kb, because we are dealing with massless particles. And one can check that under SL2C transformations, these equations remain unchanged. That is, if we transform sigma as alpha sigma plus beta by gamma sigma plus delta with this condition alpha delta minus beta gamma, these equations remain unchanged. Therefore, to fix the gauge redundancies, we can fix positions of any three punctures, let's say to 0, 1, and infinity, and that gives the dimension of this moduli space to be n minus 3. And therefore, out of the n such equations, only n minus 3 of them are independent. And one can also check that the total number of solutions obtained for this set of equations is n minus 3 factorial. And the scattering amplitude.
Sorry. I'm really sorry to interrupt you. I know you have to go on. Oh, what does this even mean? Sigma A's are locations of the punctures on CP1, if I understand.
Yes.
So given SABs, you solve for the sigma A's, is it?
Right, exactly. Yes.
And that gives you, that fixes, there's a moduli space of solutions, and then you're supposed to do the integral over that moduli space, is it? Is
yes.
That,
yes.
To obtain the scattering matrix.
But these equations will fix the solutions, right? Up to discrete choices.
Right.
And SL2Z transformation, SL2C transformations.
So that's what I was confused about. This moduli space does not refer to the moduli space of solutions. The solution is unique given SAB, is it?
Yes. Solution is unique. Moduli space is the moduli space of punctured on these Riemann spheres.
Okay, that's all. You've just quotiented out by SL2C, I guess.
Right.
Right? Huh?
Yes.
And okay. Sorry, Shiraz, excuse me, just once. And so there's a unique solution to the equations, and your integral over the punctured Riemann surface just reduces then to evaluating it for these values of sigma.
Exactly. Yeah. I mean, the whole integrations will be localized because there will be some delta functions containing these scattering equations, and the integration will be localized on the solutions of those equations.
Okay. Thank you. I'm really sorry for these.
No, thank you very much.
No, and not quite unique solutions, right? I mean, there's a discrete ambiguity whose number you've enumerated, right? This n minus 3 factorial.
I mean, so there'll be n minus 3 factorial number of unique solutions, right?
Yes, but n minus 3 number of solutions up to SL2C, right?
Up to yes.
So there are no moduli, but there's a discrete set of solutions.
Yeah,
I guess no continuously varying. Yeah.
Yes. So So yeah, so this is the way we give the representation of the scattering amplitude by this integral representation.
Sorry, okay, could you just tell me what we achieved here? So sigma, so okay, we found some solutions. So given SAB, I know what sigma and sigma b's are. There are n minus 3 factorial of them. And then what did I achieve by this? I mean, the job is to calculate the scattering matrix of a given theory, and the claim is some n equals 4 or something, that this gives you the S matrix of n equals 4. Is that what are we doing?
Yeah. So
sorry for being ignorant about the subject.
No. So n equal to 4 by that you mean this n, right?
No. I mean, what is coming out of this? What are we getting out of this?
Yeah, right now we have written down the scattering equations, and for example, if we have 3 particles, n equal to 3, then we see that there is no solution, meaning because of the SL2C, we have already fixed all the points, 0, 1, and infinity. And then if we take n equal to 4, then we see that there is one sigma that is left to be determined, and that will be determined in terms of this SAB, these Mandelstam variables. And then what we do is that we write down an integral form of the scattering amplitude, which use this scattering equation in the delta function. And therefore, for example, in this representation of the scattering amplitude, we see that so we have to solve for these scattering equations here, and this IN is the integrand, and that gives information about the particular theory that we are considering, particular theory of the scattering for whose we want to find the S matrix. So then we immediately see that because of the presence of these delta functions, the full integration is localized on the solutions of those scattering equations. And
so the loop integrals have been reduced to sums. Is that the point?
Okay. So right now we are. This is only at 3 level. There is no loop integration.
So to begin with, I did not have an integral, right? So why do I have to think of it as an integral and then sum?
I mean, this is another representation of the scattering amplitude. So what happens that, say, for example, in the usual way of Lagrangian formulation, we have to calculate a lot of Feynman diagrams. So here, this becomes an algebraic problem of finding solutions to the scattering equations instead of drawing Feynman diagrams.
But I don't yet know what IN is, right? You said it's a theory-dependent function.
Yes. So
how does one calculate?
Yeah. So
that's something easy to calculate.
There are specific properties of this IN for which we can come up with various IN, and then by guess and by a lot of studies, one can relate the IN to specific theories. And so far, there has been a huge number of theories for which we know this IN. For example, for gluons, gravitons, it will be more clear. So right now we have arrived at this integral representation of the scattering amplitude, where this dn sigma is basically the wedge product of n sigmas, and we have mod out by the volume of the gauge group, volume of SL2C, and here we have product over delta functions whose arguments are the scattering equations, and this prime product denotes that we have to remove 3 number of delta functions to maintain that gauge redundancy, and this IN is the integrand which depends on the theory, and the arguments are the scattering data, that is external states, external polar momenta, the polarizations epsilon, and also the coordinates of the functions. And under...
Sorry, are there some general properties that IN has to obey?
Yes, so general property is this one. So under SL2C transformation, this measured part transforms with SL2C weight -4. So for Mn to be SL2C invariant, first of all, it has to be it has to transform in this particular way with SL2C weight +4. So that is a necessity. And so then the question is what kind of IN or what kind of objects will have this kind of transformation under SL2C transformation.
This is the inverse transformation of the delta function, is it?
Delta function along with the measure, dn sigma also.
Okay.
Right. So one could, just to understand what the final hope might be, could one hope to classify all INs that satisfy these general properties and then eventually establish a map between such INs and Lagrangians, for instance?
Yes.
So the hope is that the space of INs is some countable or classifiable space, and which eventually maps to the space of all Lagrangians.
Exactly.
Perhaps once you specify the spins of the external particles.
Exactly. Yes.
So couldn't it even be bigger than the space of Lagrangians? Just to ask you, I mean,
yes. So there are.
Yeah.
I think. I mean, so initially when they were constructing, they could come up with various ions, and of course, most of them they could relate to Lagrangian, and then there are some ions which they gave interpretation of Lagrangians later, meaning they could be coming from higher dimensional operators and so on. So I think for PHY prescription, all the ions have been given physical Lagrangian descriptions. But now the question is, when you do for higher dimension, what do these ions correspond to?
I see.
Higher dimension.
No, I mean, I was wondering, again, sorry for being so remedial, you have to go on, but I was wondering whether one might be able to get to field theories which don't have a convenient or even in principle a Lagrangian description this way. Is that part of the hope of the program or no? That's
yes, in that way, like many of the field theories which do not have Lagrangian description, they can also be studied using this formalism.
okay. Thank you. Sorry.
However, this is an innately perturbative program. So we're only looking at theories that have a weak coupling description.
Right. Yeah.
So,
this is a tree level.
I see. So then you should have a Lagrangian. But
it should have some sort of Lagrangian, maybe a Baroque one. But
I see. Couldn't be non-local and weakly coupled or something with a consistent S-metry. Okay. Fine.
So the tree level. So this tree level stuff is coming because it's all coming from BCFW, the recursion relation. Is that what is at the back of this whole machinery? I mean, factorization.
I mean, factorization.
Basically, on-shell factorization.
Yes, but I mean, right now we are not talking about BCFW kind of factorization, but I mean, tree level is coming. I think it is by study or like by observation they could relate this to the usual tree level amplitudes.
Right, but you start with tree level. So in particular, BCFW, something that satisfies the BCFW recursion relations, and then you massage it to this form, right? I mean, it probably takes some work, but that is the source. I mean, that is the that is how how one is.
But one thing is that, right? I mean, in BCFW mostly we use gauge theories where these gauge symmetries are there, so that it has a nice structures at infinity. We can do the recursive expansion, but here it also works for scalar theories.
Okay.
Sorry, just to follow up on Abhijit's question, are there any constraints of IN that come from factorization? I mean,
yeah. So, in that way, we will expect. I mean, some properties come from the factorization that IN also factorizes into lower point IN. So, right. For example, if we take gravity, say IN plus 1, and let's take a soft limit, then IN plus 1 also factorizes into some soft factor times IN.
Right. So the hope might be that once you write down all the constraints on IN from all physical requirements, this measure condition, but also various other physical conditions coming from perhaps factorization, yes. that space can be mapped to the space of Lagrangian's modulo field redefinitions. And this would then be a completely independent way of formulating S matrices without Lagrangians.
Right.
Okay. Thank you.
But then, do you have to kind of write down all ions, or you have in mind a way to kind of recursively construct ions for all n's?
I mean, whatever IN we can come up with, we write down and then study, because all IN we do not know that if we are missing out some INs or not. So writing down all or exhausting all the possibilities of IN will be a difficult task, I suppose. Meaning, IN we can hook up IN in various ways.
No, but I'm sorry, just say, but if this is going to be a reformulation of Lagrangian field theory, then we should be able to show that every Lagrangian, that there's a one-to-one map, right? So I'm not saying it's been done yet, but presumably the eventual hope is that there's an independent set of constraints you can write down on ions, and if you enumerate them all, there's a one-to-one map between those and Lagrangian's modulo field redefinitions.
Yeah, that is true.
Yeah.
But anyway, at tree level, there's an infinite set of Lagrangians, right, Arnab? As you yourself said, you can always add irrelevant couplings of arbitrary dimension. You're not asking for any consistency beyond just some tree level scattering.
Yeah, that is right. So, I mean, INs for those higher dimension operators or for other couplings have also been worked out. Meaning, first people come up with INs and then we get to what kind of theories that may have.
Right, right. But I mean, we already know, as along the lines of what Shiraz is saying, that the set of Lagrangians is infinite, etc., etc., and we can write them down also, presumably, although you say maybe they're new field theories, perturbative ones we can discover, like this.
Yes, yes.
But you know, Sandeep, I think the first hope would be just with the known stuff to formulate some independent constraints on this IN such that you can enumerate these and establish a one-to-one map with Lagrangians. Then you've got an independent way of formulating S matrices and scattering theories without using the word Lagrangian, though you get all the good things from Lagrangians. Yeah. So, sorry to interrupt so much.
No, I agree.
Just to ask, Shiraz, you're saying that somehow like the IN should, the counting for IN should map to our counting, right? Because
exactly.
It should, because I don't care about locality anymore. I mean, you are just enumerating tensor structures.
Yeah, so there should be a way of grading IN with maximum dimension, and then that thing should, okay. I mean, I'm just free associating. I don't think anyone's done any of this, but Arnab should correct me. Yeah.
Yeah, I mean, those one-to-one correspondence or constraining the IN, I don't know if that has been done yet. Okay, so as I also mentioned that because of the presence of delta functions, this integration is localized on the solutions of the scattering equations, and this is the final form, final compact expression for the amplitude given as a sum over all the possible solutions. And this is this determinant prime phi n is coming because of the Jacobian from delta function transformations, which is given here. So let us see an example. So the first simplest example is that of what we call bi-adjoint scalar. And before that, let me define this particular factor, which is given in this way. So here alpha is a particular ordering that we have considered. It can be also canonically ordered, meaning 1, 2, 2, n kind of thing. And this is given as 1 divided by product over n such terms, where each term contains a difference of the 2 sigmas. Okay, and one can check that this particular factor transforms with SL2C weight plus 2. Under this SL2C transformation, one can check that, and therefore one copy of particular factor forms a half integrand, and 2 copies of this particular factor will form a full integrand, which will have the correct SL2C transformation. So therefore, that will satisfy that will be a good candidate for an integrand IN. Now the question is, what theory does it give rise to? And it is shown that it is found out that this corresponds to having this interaction term in the Lagrangian, where there is a cubic coupling and each scalar lives in the adjoint representations of 2 unitary groups. And the full amplitude for this interaction term is given in this way as a sum over 2 traces, 2 sum over traces, where these TAs are the generators of the unitary group, times a color stripped partial amplitude Mn alpha beta. And this IN actually stands for this Mn alpha beta, and this is called the partial amplitude. So this is an example of a scalar theory. And also we can construct.
Sorry. And then Mn alpha beta is determined how? By the additional interactions that could be present, or how?
Okay, so in the CHY, we take this integrand IN and then plug it into here in this expression. And then what we get, say for example, for n equal to 4, we'll get some kind of term 1 by s plus 1 by t. And this s and t that will come from the solutions of this scattering equation. So I mean, I have some example later. So this is the way we find out this Mn alpha beta.
You mean after doing the integral, what you get, huh?
Yes, exactly.
Okay.
I mean, in principle, we do not have to do the full integration. We only have to solve for the scattering equation. Okay. Say, for example, n equal to 4, there is only one solution because total number of solutions is n minus 3 factorial. So there is only one solution, and that is what we have to obtain.
And if you just took that partial trace thing, then this amplitude agrees with the full amplitude you get agrees with this interaction in an otherwise free theory. Is that correct? That is, you just take del phi square for the fields, and with this interaction, and what you get is what you get. Just to understand. Or
yes. I mean, free theory meaning we will have L free plus L interaction, and then the amplitude will be this, the full amplitude.
Thank you. Go ahead. Thank you.
Yes. And then we can also have amplitudes for spinning particles. And for that, we have to define a new object called Pfaffian. And Pfaffian is, in mathematics, Pfaffian is for antisymmetric matrix, it is given as square root of the determinant. So we define a 2n cross 2n matrix like this, where each of these A, B, and C is n cross n matrix. So A matrix is given in this way. It contains information about the external momenta. So off diagonal elements are given here, Ka dot Kb by sigma A minus sigma B, and diagonal elements are 0. Similarly, B matrix contains the polarization part. These epsilons are the polarizations. These are the off diagonal elements, and diagonal elements are 0. And C contains a mixed part. So this is the way we construct first this psi n. And what happens is psi n has a kernel of dimension 2, which are given by these two vectors. Therefore, the determinant vanishes, and therefore the Pfaffian also vanishes. So one defines a reduced Pfaffian by taking out 2 rows and columns labeled by I and j from this A matrix, and then take the Pfaffian and multiply by a prefactor like this. I mean, this ensures that the reduced Pfaffian is independent of the choice of I and j main. So this Pfaffian prime psi n will again have SL2C weight 2 under SL2C transformation. So it will act as a half integrand. And then if we take one copy of this reduced Pfaffian and one copy of this particular factor and plug it back into the scattering amplitude expression, what we obtain is gauge theory amplitude with a particular color ordering. And for gravity amplitude, the integrand is 2 copies of this reduced Pfaffian. So this is the way, like we can express several amplitudes in this integral representation. And of course, in the theory, there exists many other building blocks which give rise to different theories. So this is just some few examples that I have done.
Arnab, this question perhaps is way out, and we can postpone it to later. But suppose we took one of these theories, let's say a bi-adjoint theory, and put it in ADS.
Yes.
Now, there's a sense in which the S matrix of the flat space theory is analogous to the boundary correlators of the field theory, the boundary field theory. So do you know if there is a way of a similar way of expressing boundary correlators in a similar language of integral over Riemann surfaces?
Yes. So recently, I think a few months back, there were a couple of papers on this. So how they computed these ADS correlators using CHI-like prescription. One was by Misera and his collaborators, and one was by probably David Skinner and other people. So they have computed ADS correlators in terms of the CHI representations.
That's very interesting. I was wondering whether that might be a hint for what kind of string theories with these things would be due to, but I'll ask you later. Thank you.
Yeah, so here are some examples of this bi-adjoint amplitudes. So the 3-point amplitude is trivial because by SL2C gauge fixing, we are fixing all the punctures. And so therefore this is just set to unity. And for example, if we have a 4-point amplitude with these particular orderings of alpha and beta, alpha is taken to be the canonically ordered 1, 2, 3, 4, and beta we take this ordering 1, 2, 4, 3, and the answer that we get is this -1 by S12. And similarly for 5-point amplitude, we will get, with this particular ordering, we'll get this answer. And this can be worked out. And so these bi-adjoint amplitudes, they occur ubiquitously in this CHI formalism. And one important application of this is in the KLT orthogonality relation. So these relations were first discovered in the context of closed and open string theories. And later, it was shown that in the field theory limit, there exists double copy relations between gravity and Young-Mills amplitudes, where gravity amplitude can be given as 2 copies of the Young-Mills amplitude with say different ordering beta and beta tilde with a kernel between them, and the kernel is a matrix whose elements are inverse of these bi-adjoint amplitudes. So that's an important application of these bi-adjoint amplitudes. Okay, now I'll move on to the CEGM. So for a moment, let us again go back to k equal to 2, that original CHY, and we saw the scattering equations, and there is a different way of obtaining the scattering equations by introducing something called generalized potential function, which is given here. So we introduce a function as a summation over a and b running from 1 to n, SAB, these are Mendelssohn variables, log of this determinant. So this round bracket is the determinant of this 2 by 2 minors, where the sigma s are points on CP1. And now we can go to a particular coordinates chart. And so CP1, every point will have 2 homogeneous coordinates. And when we go to a particular chart, we can write them in terms of inhomogeneous coordinates by taking the ratio of the sigma 1 and sigma 2. And this becomes this determinant. So this becomes basically xa minus xb up to a sign. And the scattering equations are obtained by extremizing this potential function by taking derivative with respect to each of these x's, and we will get total scattering equations for every a, total number of scattering equations for every a. And now this can be generalized to higher dimensional projective spaces. So instead of taking 2 by 2 determinants, we take k determinant of k by k minors. And so in the CP k - 1, every point will have k - 1 homogeneous coordinates. We take k such points and form this determinant. And then we can define generalized potential by taking this summation over a1 to ak running over 1 to n, and introduce some objects like which are called generalized Mendelssohn variables, SA1, A2 to AK, and a priori they do not have any physical interpretation. They are not related to the usual Mendelssohn variables. This times log of these determinants. Although they do not have any physical interpretations, these Mendelssohn variables, but we can impose some conditions on them, like momentum conservation. That is, we take for every A1, we take a sum over rest other labels A1 to AK and set them to 0. So that ensures momentum conservation. And if we demand, like whenever 2 indices repeat, that object is 0. So that will give us massless condition. And then by take.
Sorry, Arnab. I mean, physically, what are we doing when we increase 1 to k, CP1 to CP?
So right now, I mean, we do not have any much physical insight to that. We are just generalizing the story from k equal to 2 to higher dimension. So these generalized Mendelssohn variables do not have any physical interpretation so far.
No, but at the back of your mind, you have some scattering problem that this thing should be an answer to, or not quite.
Not quite, but in this work we found an answer, like what they can stand for. So the way the CEGM introduced, this was more like a mathematical problem.
Sorry to keep interrupting, but just So to follow up on Abhijit's question, suppose I was interested in a one-loop amplitude and I was guided by string theory. The most natural generalization would have been to replace CP1 by a torus.
Right.
Has that been, is something like that also done?
Yes, that is done in the context of ambiguous string theory. I mean, there's a development, and they have computed, I think, 4.1 loop graviton and even 2 loop graviton amplitudes using these higher genus Riemann surfaces.
So there's some generalization of this form IN to a form that will live on the torus.
No, I think they do not generalize the form IN, but they modify the integration, the measured part, because now that will be on the torus. So they take moduli space of all these punctured torus.
And IN stays what it was.
Okay, I'm not 100% sure, but I think, I mean, IN may have some modification, but in general, the main modification is done in the measured part. Because now the gauge group will be defined, it will not be SLQC.
I see, but is it part of the usual CHY program to try to replace CP1s by
no.
higher genus Riemann surfaces?
No, the way loop integrand is constructed in CHY is by taking forward limit. So what they do, is that they take one higher dimension. I mean, it's an internal dimension, but basically they take n plus 2.3 level amplitude, and they join the two external legs with the with a line. That means that forms a loop. So the relation with the loop amplitude and free amplitude they do is they take n plus 2.3 level amplitude and they relate it to one loop endpoint amplitude in CHI, and that is still done on punctured dimensional spheres.
I see. So that's also sort of disappointing. It's the connection with string theory, if it exists, has not been developed.
Arnab, can I make a small comment?
Yes.
Actually, it is so the way Arnab is saying about regarding format limit is like one way to do it, but it comes with many problems. I would say that actually the part of torus higher genus surface is part of CHY program now actually. So what Shiraz is asking, that if you want to go to two loop amplitudes now for Yang-Mills, for example, you really have to look at exactly like in the string worldsheet, two genus surfaces, which is what people are doing, and it is part of CHY formulation.
Okay.
Yeah.
Thank you.
Yeah.
Yeah, okay. So the scattering equations that we obtain is again by extremizing this generalized potential function with respect to each of these coordinates xai, and therefore we'll have so many number of scattering equations for every a and for every I running from 1 to k minus 1. And for example,
can I ask a question? Sorry,
yes,
I mean,
yes.
thinking about it kind of from the string theory point of view, or ambit twister, or whatever the relevant strings are here, this sigma integral that you wrote down should be thought of as integral over the modular space of strings, or not? Not, or is it? And the question
Yes.
was that what does it mean that you are just getting delta functions? Because in string theory you would have to do the integral. All the points on the modular space would contribute. So here you are getting delta function. So how does this work?
I think the delta function is part of the integrand, Abhijit. It's just that the measure that you're doing an integral, but the integrand happens to be a delta function.
Yeah, but how is this then related to string theory? Because
it's alpha prime limit, Abhijit. It's the alpha prime going to of the Koba-Nielsen factor. So in the
I see.
That is what gives you the delta.
And then that in string, I see. In that limit, string theory integrand becomes supported only on delta functions, is it?
Exactly. But the point is that if you take alpha prime going to zero limit of the Koba-Nielsen amplitude, you don't quite get CHY. But Jacob Burjali and others showed that there are these dual string models whose alpha prime going to zero limit produces precisely the CHY amplitude. Yeah.
Okay.
And philosophically, it's like what Rajesh has been doing recently, right?
Exactly. Yeah.
This k=1 stuff, if you remember, Abhijit, that the whole integral localizes only to very special points.
Yes.
It's like again, it's because it's a free theory. Somehow in the free limit, string theory becomes this degenerate thing where the integral over moduli space localizes to discrete number of points, it looks like.
But Alok somehow is saying the limit, the quote free limit that you're saying is actually alpha prime going to zero limit.
Yeah, of a dual string
dual
string model. Yeah.
That's what we would expect also from ADS-CFT, right?
Right.
You mean alpha prime goes to infinity?
So alpha prime goes to infinity for the usual string, but alpha prime going to zero of a dual. There's a different model for
Right. Yeah. So then you would expect this is just what you would expect for free theory, right? Infinitely floppy string.
Yeah. Infinitely floppy string. Okay. I see. Thanks.
Okay. So for k = 3, here is an example.
One more tangential question. These scattering equations kind of also look like Bethe equations. Is there any relation to integrable models also?
Yeah, not that I know of. Yeah.
Okay. Thank you.
So yeah, for k = 3, we arrive at two sets of equations. So here I have called x1 as x and x2 because on CP2 we'll have two homogeneous coordinates. So x2 we'll call y. So these are the two sets of equations. And in general, moduli space on which the scattering equations are defined, we call that xkn. And that is given by the Grassmannian grkn modulo c star n minus 1. So Grassmannian grkn is the space of all k planes in n-dimensional space. So to start with, we have, let's say, nk number of coordinates, and k planes have this isometric glk. So we remove k squared number of degrees of freedom. And on the top of that, there are some scaling degrees of freedom available. We can scale all the coordinates. I mean, that is a symmetry. So we fix one of the coordinates and scale raise. So that way we'll get c star s to the power n minus 1 torus action, n minus 1 scaling, and that reduces the moduli space to k minus 1 times n minus k minus 1. And there is another way of seeing that count. The scattering equations that we just saw transform covariantly under SLKC transformations, and therefore we can fix k plus 1 number of points to fix the gauge fusion densities. So let's say here we have this n cross k matrix where these are written in the inhomogeneous coordinates. So we have n into k minus 1 total number of coordinates, and then we gauge fix k plus 1 point. We have fixed first point to 0, k plus 1th point to 1, and there are k minus 1 ways of going to infinity in CPK minus 1. So we fix k minus 1 points to infinity. And therefore, we have the number of undetermined coordinates to be n into k minus 1 minus k plus 1 point, each having k minus 1 number of coordinates. So we are left with k minus 1 times n minus k minus 1 number of undetermined coordinates, and that is also equal to the dimension of the moduli space. And with this generalization, we see the example of an amplitude. So here we first generalize the definition of the particular factor. Now this particular factor is given as 1 divided by these quantities. So earlier we had difference of the sigma 1 minus sigma 2 kind of thing, which can also be thought of as determinant of the 2 cross 2 minus, and we generalize to determinant of k cross k minus in this way. And here we have taken the canonical ordering 1 to 2n, but it can be anything, alpha, beta. And if we take 2 copies of these particular factors, that will again form an integrand for this generalized bi-adjoint amplitude. And the amplitude is then given in this way. We have integrations over these number of variables, dx ai, a running from 1 to n, and I running from 1 to k minus 1, and mod out by the volume of the gauge group SLKC. And here we have a prime product over delta functions containing the scattering equations, and prime denotes that we are removing k plus 1 number of delta functions from here. And that forms the generalization of the bi-adjoint, partial bi-adjoint amplitudes that we saw before. Now here is an example of a 5-point example. So as we saw for k equal to 3.
So in the context of thinking about from string theory, these scattering equations are just equations of motion, right?
I mean,
these are just Euler-Lagrange equation of motion.
Yeah, for example, if we consider some kind of generalized potential, then they are equations of motion. I mean, for k equal to 2, we can think of this potential as the way particles are arranged in a line, and the potential that they are facing. They are
no, I mean of the string action.
Yeah, but that no, that I don't.
Wait, Abhijit, this is localization on moduli space. So it's not equation of motion of the string. Well, the CFT. Oh, maybe I'm not understanding. I mean, the world sheet CFT gives you that IN, whatever it is.
Yes.
And then that happens to have this delta. Is that what you're saying?
No, because it's a free theory. I was thinking that the action localizes on certain field configurations, which would be some points in the modular space, and then these equations are the.
Yeah, but the localization is happening in moduli space. It's when you're doing this integral over the moduli space. Yeah, not at the level of the string world sheet action. I mean the CFT part.
Okay.
Yeah.
Thanks.
Yeah, thank you. So coming back to the 5-point example. So for k equal to 2, we can compute M2, 5, both alpha and beta we have taken to be canonically ordered, and this is the answer that we get. So there are 5 terms, and each term contains 2 Mandelstam variables in the denominator. So this is understandable. If we draw Feynman diagrams, there will be 5 Feynman diagrams for 5-point amplitude with cubic interactions, planar order 5-point amplitude. They are arranged in a plane. Every Feynman diagram will have 2 propagators. So that is here. And similarly for k equal to 3, we can compute the same object, but for k equal to 3, meaning on the CP2 with both alpha and beta canonically ordered, and we obtain this answer. And a priori, these 2 answers are very different, so they do not have any relation. But if we take these Mandelstam variables, these generalized Mandelstam variables, and substitute by the complementary set. By complementary set, what I mean is that we take this set of 1, 2, 3, 4, 5, and let's say take S3, 4, 5, and substitute by the complementary of 3, 4, 5, that is S12. So S3, 4, 5 we substitute by S12, S512 we substitute by S34, and so on. Then we see that these 2 amplitudes are equal. So by the substitution of, by substitution of this complementary set, these 2 amplitudes become equal. And so here it may seem like a coincidence, but actually this is not. It's a consequence of the isomorphism between the 2 Grassmannians, GRKN and GRN minus K, comma N. Because GRKN was the space of all K planes in n-dimensional space. So we can also think of the complementary set of these K planes, that is n minus K planes in n-dimensional space, and hence this isomorphism. And as a result, there is a duality in the moduli space of xkn and xn minus k, comma n. And in general, like if we write down this potential function sk on this cpk minus 1, and replace this k cross k minus by the complementary set n minus k cross n minus k minus, and similarly replace these Mandelstam variables by the complementary set, then what we get is the potential function for n minus k minus 1. So sk maps to generalized potential function on cp n minus k minus 1. That is for n equal to 5, we saw the mapping between cp1 and cp, meaning potential function on cp1 and cp2. For n equal to 6, it will be potential function on cp1 and cp3, and so on. So there is this duality. So from here, one thing is clear that even though we are going to higher dimension generalization, some amplitudes will be equal to the usual k equal to 2 amplitudes just by the duality of these moduli spaces. Okay, now I move on.
Sorry, you said one word. You said that you are getting amplitudes for generalized bi-adjoint scalar, right?
Right.
What is this theory? Or this is the definition?
This is the definition. We don't know what theory it is. Yes.
No, but you also said that you have an answer to what this is computing.
Yes.
So could you say what this answer is?
Yes. So I mean, right now we have given an example M35 because we know the integrand. The integrand is the 2 copies of part Taylor just by mathematical object. I mean, we are not associating any physical interpretation right now, and we can compute this amplitude. And then by inspection, we see that this amplitude becomes equal to the usual bi-adjoint amplitude defined for k equal to 2. So in that way, we are relating this.
Oh, I see. But that is just because of this Grassmannian thing, the duality of Grassmannian.
Exactly. Yes.
I see.
So what happens?
But a priori for large k and large n, it will be difficult to kind of make this connection.
Yeah,
right?
yeah. For any k, any n, it is difficult.
Yeah.
I mean, for specific cases, by using the duality between the Grassmannians, we can relate some theories to the usual bi-adjoint theories, but not for any other.
So your point of view is that for general and general k, you are getting some interesting mathematical object, and let's study that object.
Exactly. So we already saw that k equal to 3 and equal to 5, we have an interpretation in terms of the usual. So that motivates us to study k equal to 3 and equal to 6. What is the next object? I mean, we do not know a priori what it will correspond to. But yeah, before that, I'll review some mathematical things, tropical Grassmannian.
No, but a priori, I mean, I can see the way you are trying to connect it only through this Grassmannian duality. So from that point of view, the stuff that should relate to k equal to 2 is basically where k is equal to n minus whatever 2 or something, right?
Yeah, k equal to 2n, so it will relate to n minus 2 comma n.
Yeah,
so for example, 2 6 will be 4 6.
Right, but do you hope to relate something that is not this also, or just this?
something not this. For example, GR36. It is
yeah,
kind
that's
of
okay. Good. So you will say what you're getting there, right?
Yes, exactly.
I see. Okay, thank you.
Yeah. So okay, I'll review this Grassmannian. So K cross K minus of this GRKN, we denote them as Fluker coordinates. I mean, this is another notation we are introducing, Pi1, I2 to Ik. So these are K cross K minors. And these Fluker coordinates or these minors, they satisfy some relations known as Fluker relations. So what we do is we take the product of two Fluker coordinates and antisymmetrize K plus 1 indices. And they can be shown to be 0. For example, for the case GR2n, this is what we get for Fluker relations. Here, we have kept I fixed and antisymmetrized over three indices J, K, and L. And this is what we get. And we will also use some tropical geometry things. In tropical geometry, what we do is we replace multiplication by addition. That is A times B, we replace it by A plus B. And addition is replaced by minimum. So capital A plus capital B, we replace it by minimum of A and B. And in that way, by using this tropical geometry, from the Fluker relations, we obtain tropical polynomials, meaning these are the Fluker relations we have, and that we can write as a minimum of Wij plus Wkl, comma Wik, Wjl, and so on. And we can see that under this shifting, Wij to Wij plus Ai plus Aj, this remains unchanged, and that is again a manifestation of momentum conservation in the scattering amplitude, as well as from here this amounts to the scale invariance. We can scale all of the p's by certain value, and still that equation remains invariant, and that is the manifestation of this shift symmetry here. So to give an example with the 4-point amplitude, so GR2524, we have one Fluker relation, meaning although we have a bunch of Fluker relations, not all of them are independent, and getting a count of how many independent Fluker relations are there, that is a complicated task. So in case of GR24, it can be shown that there is only one independent Fluker relations. So this is the Fluker relations we have, and we take the tropicalized version of that, which is given here. And then,
sorry, Arnab, I mean, now you are talking about this tropical geometry stuff. So was that also present earlier in the CHY case in some form?
Yeah, in the
or this is some new thing that you're introducing?
Actually, in the CHY case, I think, I mean, the people, Alok and other people who are doing this positive geometry, they use this tropical geometry thing, tropical Grassmannian, because this associahedron and these polytopes, they can also be thought from, I mean, they can also be studied using these tropical geometries and Grassmannians. So this associahedron.
My rough kind of picture of tropical geometry is that it takes the worldsheet, which is fat, and makes it thin, and makes it into trees, right?
Thin meaning makes it compactified?
No, I mean makes like makes into a tree graph. It thins the world.
Yeah. I mean, yeah, that is another way of looking, meaning that is related. Here also, we are doing the same thing, meaning the entire CHI program can be recast into the language of tropical Grassmannian, and that will be GR2n.
Okay.
So, I mean, yeah. So here we will see that example. Say, for example, GR24 for 4-point, we have this Fluker relations, and then what we need to find is tropical hypersurface from these Fluker relations. So tropical hypersurfaces are obtained when at least two of the terms in this tropical polynomial simultaneously attain minimum. So, and we'll have three such conditions. That is, here we take W13 plus W24 is equal to this one, which is less than this one, and there will be two other combinations. So there will be three total relations, and then we have to find out the solutions to these tropical hypersurfaces, and the solutions, let us choose a basis W12, W13, W14 in this way. Say Wij for I less than j in this lexicographic order, and then we find the solutions of these tropical hypersurfaces from these equations, meaning from equalities and inequalities both. So for example, here E1 refers to W12 being 1, rest are the 0. So that satisfies this relation. So here we have 0 equal to 0, less than 1. So this will be solution to this equation, and so on. So all total we have found 3 such solutions, and then we are interested in the positive part, because positive part is what relates to the planar amplitude. Now positive hypersurfaces are those whose defining terms have opposite signs, because here note that we have this correlation and there is a relative sign here, and while we tropicalized we lost the information about sign. So that sign information goes into which tropical hypersurfaces are positive and which are negative. So when we equate, meaning when we take 2 terms equal whose defining which differ by a relative sign, for example this one and this one, that forms a positive tropical hypersurface. So out of the 3 solutions here, 2 will be positive and 1 negative. And here, so this E1 refer to these 2 being equal, so that is a positive hypersurface, and this E3 refer to these 2 being equal, that also refers to a positive hypersurface. But if we take this one and this one equal, that is given in the second relation here, W12 plus W34 is equal to W14 plus W23, then that becomes a negative tropical hypersurface. So we'll discard that. So the solution that we'll be interested in is E1 and E3. And then we have the Mandelstam variables, the basis of Mandelstam variables given in this way, S1 to S13. There are 6 of them. And we know in 4-point amplitude, like there are 3 Mandelstam variables, although they are related by a relation, but there are 3 S1 to S13, S14. And these things, say S23 by momentum conservation, will be equal to S14 and so on. So we can write down 4C2, that is 6 number of Mandelstam variables, and then take the dot product of y with respect to dot product with this E1s. EI is here to the positive solution, and that gives the amplitude. So 1 by E1 dot y. So E1 dot y, that picks out S12. So in that basis, so we have written the basis of Mandelstam variables in the same ordering as Wij. So E1 dot y will give S12, whereas E3 dot y will give S14, and that will be 1 by S plus 1 by T. And these 2 diagrams, these will be the planar diagrams. And the negative hypersurface, that would give S13, that was the non-planar. So that we will not take into account. Okay, so obtaining tropical hypersurfaces for general GRKN using this above method is a bit complicated. So we will follow cluster algebra to get a systematic prescription of finding out these amplitudes. Okay. So I hope this was clear. So now let us come to cluster algebra. And clusters can be defined as quiver diagrams, which are oriented graphs equipped with arrows connecting different nodes. And each node is assigned a cluster coordinate. And this is explained by some examples. Here we consider GR2n cluster algebra, which can be represented by triangulation of n chord. And in this picture, we have considered a pentagon. And the triangulation means drawing the chords which do not intersect and completely triangulate it. So for a pentagon, we can completely triangulate a pentagon using these 2 chords. And we can write down a cluster quiver associated to this triangulated pentagon. So here we start from an edge which is denoted by 1, 2 here, and move in anti-clockwise direction. So from 1, 2, we go to 1, 3, and from 1, 3, we have 2 ways of going, 1, 4 or 2, 3, and so on. And going from an edge to another edge is forbidden. So we will not make that move. So this is a kind of pictorial representation of this triangulation which is given here, and this we call cluster quiver. So in this quiver, there are like total 5 frozen nodes corresponding to the edges of this pentagon, and 2 unfrozen nodes. And unfrozen nodes basically will be the ones on which we will mutate. So mutation pictorially means or in the case of GR2 means going from one Feynman diagram to another. So here what we do is we collapse these 2 points and extend this in different direction. So from S channel we go to T channel and so on. And we will call these Fluker coordinates as A coordinates. Again, a change of like a nomenclature here. So these we'll call A coordinates. Some will be unfrozen and some will be frozen. Now, number of unfrozen coordinates will be equal to the number of Feynman propagators that we can have in a diagram. So here is an example of mutation. So mutation basically means going from one triangulation to another, or in terms of the clusters, going from one cluster to another. So mutation here, what we have done is we have mutated on this 1,3 chord and replaced it by 2,4, because this 1,4 is compatible with both 1,3 and 2,4. By compatibility, I mean they do not intersect. So this is one cluster corresponding to this triangulation, and we mutate on this 1,3 and we get 2,4. And everything can be done without drawing these triangulated pictures in a different way, meaning as we'll explain by more algebraically. And for that we need this thing called exchange matrix. So we define this matrix Bij. Bij is equal to the number of arrows coming from I to j node minus number of arrows from j to I node. So for example, if we consider these two nodes, then B12 to 13 is +1, whereas B13 to 12 is -1. So Bij can be either 1, -1, or 0. Okay, and then if we consider these two mutable nodes, so in the previous example that would be like 1,3 and 2,4, they will be related by this relation, where these A's are the corresponding nodes or A coordinates, mathematical A coordinates. And so actually this, so here there is an example. So 1,3 and 2,4, we have mutated on 1,3 and went to 2,4. So 1,3, 2,4 is following this equation, we get this relation, and one can check that these relations are again nothing but the Fluker relation. So for this example, for this mutation, 1,3 and 2,4 was this followed from this Fluker relation P1, 2, 3, 4, P1, 2, P3, 4, where 2, 3, 4 were anti-symmetrized. So the basic idea is, given an initial cluster quiver, we can find all other quivers by applying these mutation rules, and this holds for general GRKN. And if there are finite number of such quivers, then the cluster algebra is finite, meaning if after finite number of mutations we come back to the original cluster we started with, then the cluster algebra is finite, otherwise they are not. And it is known that cluster algebra beyond GR4, 8 are not finite. Okay, so now I mean these rules can be made more refined, more sophisticated. So we define these chi coordinates in terms of the Fluker coordinates. So these are xi given as aj raised to the power bji product over j. So for example, I mean we know this bji. So for example, in the previous cluster, so here we can associate x1 and x2 to these unfrozen nodes 1, 3 and 1, 4. So x1 will be 1, 2, 3, 4 divided by 1, 4, 2, 3, and x2 will be same. And then we can apply the rules of mutation on these xi and xj, x1, x2. So the mutation rules in terms of the chi coordinates will become this. So if we are mutating on kth node, then xk prime will be nothing but xk inverse, and others will take this form. So this is an example of a GR25 cluster algebra. So this is the first quiver we started with, x1 to x2, and then we mutated on x2, then we went to the next quiver, and so on. And after 5 such steps, we came back to the original cluster. So that says that GR25 is finite. And this is another representation of this cluster algebra for GR25. And then the relationship between this chi and A coordinates, we can invert them to express in terms of the Fluker coordinates. the relationship between chi and a coordinates can be inverted to express the Fluker coordinates in terms of the xi variables. Earlier we saw how to write xi in terms of the Fluker coordinates, but we now reverse it, and there's a systematic way of doing that by defining some matrix, W matrix and gauge fix and find. I mean, here I'll present some examples. So in the case of GR25, earlier we obtained xi in terms of this Pij.
Sorry, Arnab.
Yes.
Sorry. So this here you're talking about GR25, right? But you said you will also talk about GR36.
Yes. That I talked.
You are yet to do that, right?
Yes.
Okay.
I mean, I just wanted to review this GR2 a bit so that when I go to GR3.
I was interested in asking basically what is it that you are calculating there?
In GR36.
Yeah.
Yeah, in GR.
But yeah.
So yeah, I'll come to there.
Yeah. Okay.
So I mean, let me quickly finish this story. So GR25. So we have obtained the Fluker coordinates in terms of this chi variables, xi coordinates, and then we tropicalize them. So tropicalization gave these relations. So Wij's in terms of this x1 and x2 tildes. Now now the idea is we plot this Wij's or plot these functions in this x1 tilde and x2 tilde plane. And what we see that all these functions are not continuous everywhere. There are regions of discontinuities or boundaries of discontinuity. So tropical minors are piecewise linear functions in this x1 tilde, x2 tilde plane. Each function is a tropical hypersurface. Because earlier in the GR24, we found out tropical hypersurface in a different way, meaning more by calculating explicitly. But here it gives a ready-made prescription of finding tropical hypersurfaces. And union of these hypersurfaces gives rise to a fan with 5 domains of linearity separated by 5 rays. So these rays will be basically boundaries of discontinuity for these functions. So for example, W24, this is minimum of 0 x1 tilde. So in this quadrant, when x1 tilde is positive, W24 is always 0. But when x1 tilde is negative, then then it will be this full quadrant. In that way, we now arrive at these 5 rays. And these 5 rays are given here as E1, E2 minus E1 minus E2, E1 minus E2, where this E1 and E2 are the 2-dimensional vectors, 1, 0 and 0, 1. So now, if we know these 5 vectors, say for example, E1, which is x1 tilde 1 and x2 tilde 0, x1 tilde 1 and x2 tilde 0, we know Wij's. So from example, by putting the values of x1 tilde, x2 tilde, we can find all the Wij's. So here is an example. Here we have found out the Wij's for the corresponding E1. So E1, so I mean, we have to make use of this shift symmetry of Wij, and then we get this value. And we call this EV of E1. So here it means that W12 is 1, rest others are 0. And then, as before, we had this variable y, which contains the basis Sij, and when we take the dot product of y with this EV of A, we get the corresponding Mandelson variable. For example, here EV of E1 dot y, we got S12, and the amplitude, the CHY amplitude by adjoint amplitude, is then given in terms of this tropical geometry thing. That is, we take sum over all the clusters, and then we take product over all 1 over EV of EA dot y, all the compatible sets. And then we obtain this answer. This answer was what we saw previously. Okay, so that is the idea. We have to find the ray vectors and dot with the corresponding Mandelson variables, meaning the basis of Mandelson variables, and that will pick out the poles. So the question is how to find the compatible sets, meaning how do we know which vectors are meaning which 2 ray vectors are compatible, and that is known from looking at the cluster algebra. So this cluster algebra can be represented in terms of a polytope, which is called cluster polytope. So in GRKN algebra, every cluster has k minus 1 times n minus k minus 1 number of mutable nodes. That is, for GR25, we saw that there were 2 mutable nodes, k equal to 2 and n equal to 5. So 5 minus 3, we got 2 mutable nodes. If we consider GR26, we'll have 3 mutable nodes. And mutable nodes basically referred to as the number of propagators appearing in this Feynman diagrams with cubic interactions. And this is also the dimension of the corresponding cluster polytope. So for GR25, we have a 2-dimensional associahedron. So ray vectors are normal to the facets, which are co-dimension 1 boundaries of these cluster polytope. And each vertex of the cluster polytope is in 1-to-1 mapping with the Feynman diagram. So again, here is an example of GR25 associahedron or cluster polytope. So these facets are normal to the ray vectors. So number of ray vectors will be equal to the number of facets that a polytope has, and the vertices actually correspond to the Feynman diagram. And GR25 algebra is also called A2 algebra because it has the structure of the A2 Dynkin diagram, x1 to x2 in that way. And the compatible set of rays are found by looking at which facets share common boundary. In this case, the common boundary is the codimension 2 boundary. So, for example, E1 and E2, they share a boundary, and similarly E1 and E1 minus E2, they share boundary in that way. So here is the set of all compatible ray vectors. So if we know this, we know like which Mendelssohn variables or which propagators are compatible, come together in a Feynman diagram. So here's a summary of the setup. So given a cluster algebra, we can generate all ray vectors by mutation. Ray vectors are mapped to the corresponding Mendelssohn variables in the kinematic space, and compatible sets of ray vectors give information about the singularity structure of the S matrix by determining which propagators are compatible in respective Feynman diagrams. And boundaries of the cluster polytopes are lower dimensional polytopes. So for example, here this boundary, this codimension 1 boundary, that refers to A1 subalgebra, that is GR24 subalgebra. In that way, every boundary refers to lower dimensional polytopes and represents subalgebras of the given cluster algebra. And these subalgebras, they basically capture the properties of factorizations of S matrix. So in general, GR2n is associated with AN-3 cluster algebra, and every cluster has n-3 mutable nodes. It follows from k-1 times n-k-1. So it has n-3 mutable nodes, and there are n into n-3 by 2 number of ray vectors. That is also equal to the number of independent Mendelssohn variables that we will have. And corresponding cluster polytope is n-3 dimensional associahedron, and this cluster algebra is related to 3-level n-point S matrix in planar phi cube theory. And this is the relation with the CHY. So GR2n cluster algebra will be related to CHY. And here is an example of this A3 polytope, which captures GR26 6.3-level amplitude. And it has total 9 facets, 9 codimension 1 facets, out of which 6 are pentagons, and they represent A2 cluster polytope, A2 subalgebra. And 3 others are quadrilaterals, which correspond to A1 cross A1 subalgebra. And there are 14 vertices that are also related to the 14 Feynman diagrams that we get in the 6-point amplitude. Okay, I'll introduce some worldsheet coordinates here, which are called dihedral coordinates. So this potential function that we saw can be written in this way. I mean, we saw it earlier, and here we have just replaced the determinants by these Lucas coordinates, and they can also be written in much more nicer or compact way as V alpha log of U alpha, where the V alpha actually form a set of bases in kinematic space. And this basis is the same as we saw before. For example, for 2,4, we saw V alpha was this basis of 6 or 3 vectors in that way. So V alpha form a set of bases in kinematic space. This basis is same as obtained from the ray vectors in the given cluster algebra. And U alpha are known as dihedral coordinates. And also, just like we had the kinematic polytope in the kinematic space, we also have a polytope in the worldsheet. And this worldsheet polytope is coordinatized by U alpha. So here, I mean, once we identify the basis of Mendelssohn variables, then just by identifying this S, meaning just by equating these two sides, we can find U alpha in terms of the Fluker coordinates. And basically, they will appear as some ratios of these P's, these Fluker coordinates. And these dihedral coordinates, they satisfy these relations where this A parallel B is called compatibility degree from A to B. So in the worldsheet polytope, the facets are given by the parameterization U alpha, that corresponding UA going to 0. And the other facets which share the same boundary, they will be compatible. So if A parallel B is 0, that means the two facets are compatible, otherwise they are not. And demanding that UA are positive, we can immediately see that U can lie between 0 to 1, and this gives a binary realization of generalized associahedra. And just to emphasize this point, so we have here GR26 amplitude whose basis V alpha is given by this total 9 elements. And corresponding to this V alpha, we can find this dihedral coordinates here. So these are given. So this notation is nothing but the determinant of 2 by 2 matrix, that 2 by 2 minus that we have. So there are total 9 such dihedral coordinates. And for example, for this binary geometric realization, let's say U13. So I mean, it's a bit of nomenclature. So we will refer to this dihedral coordinates as Uij. So U13, which corresponds to this S12, is here 3612 by 1326. And then when I mean this relation, this constraint for U13 will read as this. So, and it is again a consequence of the Fluker relation. So whatever follows, everything is almost following from Fluker relations. So when you take U13 to 0, meaning when you go to that facet, U13 going to 0, that means the punctures 1 and 2 are colliding. And when 1 and 2 are colliding, that means U13 goes to 0, and one can check that the rest other non-compatible facets, which are coordinated by these, they go to 1, because 2 will be replaced by 1 here, and that will go to 1. Similarly, U25, U26, that will also go to 1. And that brings us to the geometric factorization properties. So in GR2n, in general, these Uij's are given in this way. I mean, this is what we have actually found out from there. So this is the way we have given the Uij. And these ij minus 1, so these are like the z coordinates of this moduli space, positive part of this moduli space M0n. Now U space has the advantage that U space forms a compactified space because it is constrained from between 0 and 1. So we call this U space as compactified space, which is given as M bar positive 0n. And there are n into n minus 3 by 2 codimension 1 boundaries of this M bar space, which are denoted by Uij equal to 0. And what happens at the boundaries is the punctures zi to j minus 1, they pinch together on the left, and the other punctures, they pinch together on the right, resulting in the factorization of the polytope or worldsheet associahedron into the left and right. And similarly, in the kinematic space, this amounts to, when we take Uij equal to 0, go to the boundary in the worldsheet polytope, we go to the boundary Xij equal to 0, and now these Xij's are the Mandelstam or kinematic variables. Xij to 0 in the kinematic polytope. And there we perform the unitary recurve, that is, find the residue on that particular Mandelstam variable or the residue of that Mandelstam variable going to 0. And at these boundaries, we see there is the factorization of the kinematic polytope into the left and right. Okay, now I'll come to the one loop amplitude, the GR36 part. But before that, if there are any questions, I can. Okay. So now,
sorry, Arnab, just let me ask you, how much time do you, how much time would you need to finish?
Okay.
Do you think 10 minutes would be possible?
Okay, I'll try to wrap up.
10-15 minutes, if that's okay. Yes.
Yeah, sure. So okay, so here is a GR36 amplitude. So this is the initial cluster of GR36, and by mutations we can go to other different clusters. So GR36, we have a total 16 ray vectors, and so what happens at GR36 meaning 63 number of total A coordinates we have. Out of that, 6 are frozen and 14 are unfrozen. But because there are 16 ray vectors and the ray vectors are associated to A coordinates, we need 2 more A coordinates, which are now quadratic A coordinates, which are given in this way, Q1 and Q2. And here earlier we saw the potential function, okay, and this potential function we now modify to include this Q1 and Q2 here. And so we introduce 2 additional Mandelstam variables, SQ1 and SQ2, and then the momentum conservation also includes this SQ1 and SQ2. And so using that, we repeat the same process as before. And we find for each of these ray vectors, we have corresponding Mandelstam variables. And this is the set of Mandelstam variables that we have. VA, so these are generalized Mandelstam variables, set of 16 variables, where T and R are defined in this way. And originally, in the GR36, we had 14 unfrozen coordinates, meaning 14 variables. And these 14 variables are because that earlier there were constraint relation between this T and R, and which form this like it's a bipyramid facet. But by introducing this SQ1 on the left hand side and right hand side, so now we see on the left hand side there will be 3 SQ1, and on the right hand side there will be 2 SQ1. So that will break that constraint, and therefore we get 16 variables. Okay, and so what happens in the kinematic space elements? VA H out a 4-dimensional polytope because GR36 is associated to D4 polytope. Okay, this H out a 4-dimensional polytope which has 16 codimension 1 boundaries and has 50 vertices, and these 50 vertices will correspond to the 50 Feynman diagrams. And so this is the D4 diagram. I mean, so GR36 is related to D4 cluster algebra, and this is given in this paper by Arkani, Hamed, Hayes, Salvatore, and Thomas. The DN cluster polytope is an n-dimensional polytope with n square facets, and it is related to n.5 cube amplitude at 1 cube. And again, on the other hand, cluster string integrals provide stringy canonical forms for the generalized associahedra of a finite type cluster algebra. And in this work, what we do is alpha. We take the alpha prime going to 0 limit of D4 cluster string integral, which gives a 4.5 cube amplitude at 1 loop. We map the singularities of this D4 polytope to the generalized Mandelstam variables of the modified 3,6 CEGM amplitude and interpret the latter as one loop integrand of phi cube theory. So here's a short summary of the D4 polytope. So D4 polytope has 16 facets, out of which 12 facets correspond to the A3 subalgebra, and the remaining 4 facets correspond to A1 cross A1 cross A1 subalgebra. And these A3 facets, so we label the facets by the kinematic variables, which are labeled as x1 to x4, x1 tilde to x4 tilde, and then xij's for both ij adjacent as well as ij non-adjacent, mean non-consecutive. So A3 facets, there are total 12 A3 facets which are labeled by this x1 to x4, x1 tilde to x4 tilde, and xij for I minus j mod greater than 1. And the rest of the 4 A1 cross A1 cross A1 facets are labeled by this. And then in this paper, Arkani Hamed's. Yes. Yes.
So one question. So I guess one should think of this, the fact that this is loop now as opposed to tree, is because if you cut the loop, you get 2 extra vertices popping out, right?
Exactly.
So and this is also related to the string theory picture where you say you either think in terms of genus 1 or you think in terms of 2 extra punctures.
Exactly.
Is this?
Yeah, this is it. So when you go to these A3 facets, we basically cut the loops, and that will amount to taking the forward limit on the loop amplitudes.
Right, but I guess the point is that it is even with that, it's not quite GR2 n minus n plus 2, but rather GR3 n plus 2 or something like that, right?
Yeah,
because that's what we are doing. GR3.
That will be GR26 actually. I mean, when you go to this A3 facets, A3 is related to GR26. Yeah,
so is drawn here.
Sorry?
A3 is what you have drawn here?
No. Okay, A3 is not what I have drawn here to go. So this is when we cut a particular loop. So GR36, that is related to 4-point amplitude. Okay, and when we cut, we get 6.3 amplitudes.
That's like going to the boundary of GR3, C to GR2, C.
Yeah.
But
so going to one particular boundary of GR36.
But if you stick to GR3C, then you are actually exploring the loops.
Exactly. Yes. Yeah.
Is there any relation? Do you have any kind of understanding of why this should correspond to CP2? Because as Shiraz had pointed out, should be the torus that should underlie all this, right? But it's like a generalization in some other dimension, which is still giving you GR3. So
right. That
kind of.
Yeah, I mean, we are making an identification. I don't know the underlying reason why this should be. Meaning,
okay.
I mean, basically we exploit the fact that GR36 is related to D4 cluster algebra, and D4 cluster polytope captures the loop integrands as stated by Arcani-Ham and Hayes, Salvatore, and Thomas.
There is no direct picture.
Yeah, there's no direct picture emerging.
So, like for example, if I were to ask you what would be GR416, you wouldn't be able to tell me, right?
Yeah, I mean, GR416 is an infinite cluster algebra. So, I mean, no one knows.
No, but it could be like a 2-loop 14-point or a 12-point diagram, something like that, right?
No. General,
or not,
it does not.
It's not. You can say that, right?
Yeah, it is not known. What in general it will be. Yes.
Okay.
So the variables, so the 16 variables are used to draw the Feynman diagrams in these configurations. I mean, there are some redundancies because this diagram comes with another counterpart where these variables are replaced by the tilde variables. And yeah, I apologize here for the mix of notations. I mean, this is a screenshot of this paper. So, I mean, we are using X variables, whereas here Y variables are present. So, I mean, there's a doubling of the diagrams, and also it contains tadpoles and other non-physical, meaning which in physical amplitude should be removed. But nevertheless, this captures all the loop diagrams that will possibly come in the 4.1 loop amplitude. So in this work, what we do is we use the U coordinates, because U coordinates were obtained from the cluster string integral, and also we have a way to find out U coordinates from the Mandelstam variables V alpha. So we use that U coordinates to relate these 16 variables with the generalized Mandelstam variables. And once we have this identification, we can draw the Feynman diagrams using these generalized Mandelstam variables. And in that way, we obtain this relation that this GR36, this amplitude, although it is modified because we introduce 2 more terms. So this modified amplitude is related to 1 loop integrand of 5 cube theory, 4.5 cube theory. And every cluster will have like 4 mutable nodes, because in the 4.1 loop, 1 loop 5 cube theory, like every Feynman diagram will have 4 number of propagators. So we start with an initial cluster and assign the ray vectors to be the basis vectors in 4 dimensions, and then we mutate to generate all other 16 vectors. And so this is the association of the ray vectors with the Mandelstam variables. So once we know this relation between the ray vectors and Mandelstam variables, we know the compatibility relation that gives which ray vectors are compatible, meaning which ray vectors come in particular clusters. We know like all the Feynman diagrams. So here are some examples of the clusters of D4 cluster algebra. And so there will be 50 such clusters corresponding to 50 Feynman diagrams. Yeah, I'm almost done. So I'll just talk about some factorization properties that when we go to these boundaries, xi or xi boundaries, that will basically be like cutting the loop corresponding to xi or xi tilde and introducing these plus minus L coordinates between I minus 1 and I. So that will basically be 6-point amplitude with the 2 external states introduced which carry momenta plus minus L. So for example, if we go to the loop if we cut the loop x1 equal to 0, go to that boundary is in the worldsheet picture, that is equal to going to u1 equal to 0, and the other incompatible variables will go to 1. So if we now write down the potential function, log of 1 is 0. So I mean, from the full potential function, this looks like x log u kind of thing. So either u1 goes to 0, then that term drops out, or if x goes to 0, because x log u, both x and u going to 0, that will also log out because of the scaling. So finally, when you take u1 going to 0, we get this potential function, and this has all total 9 terms. And this potential function actually mimics the A3, the 6-point potential function, because it has this 9 terms. And these are the diagrams that we obtain when we cut the loop x1 equal to 0. And so there are 14 such diagrams corresponding to the 14 vertices of the A3 polytope. And in this limit, we can readily see the relation between the x variables and the ordinary Mandelstam variables. So here, these 14 diagrams correspond to this this amplitude M26 with this order -1, 2, 3, 4 plus. And here we have associated these 9 x variables to the usual Sij, the Mandelstam variable. So we get some interpretation in that forward limit. And also we have studied soft theorems. So single soft theorem is not very interesting. I mean, so this is a single soft where the soft limit is taken in the sixth external leg of a 6-point amplitude in M36, and this is what they obtained, which has an interpretation of A2 subalgebra, but this subalgebra is not at the boundary of the polytope, but they lie somewhere inside. But double soft theorem is interesting because that has some nicer interpretations. And this is the expression of double soft theorem, where this can be expressed as like a 2 single soft factors. So here we have taken the double soft limits in the 5th and 6th, or n-1 and n external legs for arbitrary k, and this is the result that we obtain. Importantly, the scaling of this double soft factor, it goes like 1 by tau to the power 3 k minus 1. And in the case of single soft factor, it goes as 1 by tau to the power minus k minus 1. So in that way, these soft factors are a bit unusual because they don't have the simple pole structures as Weinberg soft factors. But nevertheless, we can give some interpretations for double soft theorem, particularly in the case of GR36. So double soft factorization captures this codimension boundary, codimension 2 into k minus 1 boundaries of GRKN. Now for k equal to 3, the double soft factorization will come from codimension 4 boundary. And we know that GR36 something that we are considering is also 4-dimensional. So double soft factor basically probes the amplitude in that particular limit. So if we take soft factor in 5th and 6th external states that we have found out, and then we can express them in terms of the x variables of Arkani, Hamed, eta. And we find this term. And actually, in terms of the cluster algebra, that corresponds to a subalgebra. That is A3 subalgebra, which is associated to the x31 equal to 0 facet. And in the limit, in the leading limit, these Feynman diagrams survive. So here, this is the limit x31 going to 0 on that particular facet. Okay, I have reached the end of the talk. I'll just summarize what we have done. So in this work, we have studied CGM amplitude for k equal to 3 and equal to 6. And we use the relation between GR36 and D4 cluster algebras to map the generalized Mandelstam variables of this modified 3-6 amplitude to Feynman propagators appearing in one loop integrand in 4-point S matrix of phi cube theory. And by going to the boundaries, we have studied the factorization properties like xi and xi tilde going to 0 facet is associated to the forward limit of this one loop amplitude. And also in the paper, we have studied other boundaries, and in all other boundaries, what happens? We get back k equal to 2 moduli spaces, the original CHI moduli spaces. So, I mean, going to say different boundaries, we get back tree-level amplitudes. They may be lower point tree-level amplitudes, but that we have studied in the paper. And we have also studied soft factorizations of GR36 amplitude. In particular, we found double soft theorem for adjacent external states has a sub-algebra structure, as we just mentioned, by restricting the polytope, the amplitude to particular facets of the dipole cluster polytope. And here are some questions. I mean, the diagrams that we drew, they contain tadpoles, and Feynman diagrams that we obtained from the cluster variables contain Salvatori, Thomas, D and bar. Am I audible? I'm getting some message.
Yes, we can hear you.
Okay, sorry. Arkani, Hamed, Hayes, Salvatore, and Thomas consider D and bar polytope. Basically, they halve the number of variables by setting this xi minus xit equal to x0, which are positive, and they restrict the tadpoles to this facet x0 equal to 0. Now the question is, can we do similar thing for these CGM amplitudes? And then the pertaining question, what happens to the other GK amplitudes? Can we give some physical interpretations? I mean, so far the answer is not known, and there have been some progresses like by Cachazo and Early in terms of something called root polytopes, but they are yet to be studied in more detail. And the last question is that n equal to 4 super Young-Mills has GR4 in cluster algebra. So can we relate the k equal to 4 CGM amplitudes to n equal to 4 super Young-Mills amplitudes? That's the question. And with that, I'll stop. I'm sorry for going over time.
So maybe we can first clap, unmute ourselves and clap. Okay, so thanks a lot, Arnab, for the very clear and very nice talk. Questions? Maybe I can start. In the context of this, the last part I didn't follow all details, so I apologize for I'm asking something stupid. But in the context of this one loop amplitude, if I understood right, what you were doing was to obtain the integrand of the amplitude.
Yes.
Is this right? Now, in a situation where you obtain this integrand on the torus, integrating over the remaining moduli would also produce the integral. You know, that's one of the great things about string theory, right? You get the integrand and then also the integral by doing the moduli space integral.
Right.
Is there any analog of that in this setup? Is there a natural way of doing the integral in this setup?
Yeah, I don't think so. I mean, so far what they consider is only the integrand, because doing the integration will require, because these are field theory amplitudes, I mean, the questions about renormalizability and those things will come. Regularization.
Yeah, so, but even up to that, just to get to the, let's say there are divergences at some short distance or something, but, you know, if you were on the torus, you put these sigmas at various points, you wouldn't, you know, unlike on the sphere, I presume that if the CHY kind of program goes forward on the torus, you said that on the sphere, these locations were all completely determined.
Yes.
Right? On the torus, presumably that will not be the case. There will still be some undetermined thing. So there'll be a family of solutions, and then integrating over that family produces the integral of the loop, I would imagine.
Right.
I mean, the moduli would be associated not just with the insertions, but also with the torus itself. That combined space, the integral would produce that loop. And then maybe, you know, there's a question of understanding why that's not infinite. Maybe there's a divergence in that integral, and you have to understand that, and so on. That's a separate issue. But just at least obtaining the formal integration expression. Of course, you can take this integrand and integrate it, but where that case comes about naturally in this framework.
Yeah, I mean, I think here they only focus on the integrand, because integral, I don't know of any method where they have also done the integral on the loop amplitude.
Okay, I see. One more question. Again, maybe ill-defined. You know, an integrand of a Feynman diagram, that's defined only up to, I would imagine, total derivatives. Because two different integrands that differ by total derivatives give you the same integrand.
Yes.
So when you say you get the integrand, you're getting it in some particular convention, with some particular gauge or so.
Yeah, so I mean, one feature of the CHY is that even though Lagrangians differ by some redefinition or partial derivatives, but what CHY computes that amplitude is unique because CHI is computing amplitude. Now, in terms of loop integrand, okay, I guess there may be some gauge fixing done. Meaning, I'm not very sure because here the answer. I mean, here we have taken a particular answer of 5 cube amplitude,
right?
And we have associated the variables to the loop variables here. And yeah, if we change the Lagrangian, meaning by adding some terms, then this association could not hold. Might have been different.
Okay. Thank you. Any other questions?
So one question. So the scattering equations that you had for GR 3,6,
yes.
What sort of solution space they had? How many dimensional? I mean, in the previous case of this CP2 thing, you only had discrete number of solutions, right?
Yeah. So I mean, count on the number of solutions is not known.
But are they discretely many, or you have a continuity to be integrated over?
Yeah, I think I mean they are discretely many. I mean, maybe there is an upper bound on the number of solutions, but in general, the exact number of solutions, like in the K2 case, we had n minus 3 factorial number of discrete solutions. That is not known. But in our earlier work, we did the double saw factorization.
Shuman, maybe you can mute your computer, Shuman. Yeah, go ahead, please, Arnab.
Yeah. In the soft limit, when you take one external state to be soft, then we have a count on the number of solutions, meaning in that particular limit, how many solutions contribute to the soft limit. That we saw, and those were discrete solutions. So in general, I do not know of the nature of the solutions, but I predict, but I think they are discrete, not continuous. But the total number of solutions is not known.
I see. So expecting that the solution space should just match up with the modulus space, somehow string modulus space is too naive, I guess. It's not how that is working. Okay.
Right.
Okay, thank you.
If it had worked that way, you'd say just integrate over the solutions and that produces the integral.
Right. Yeah, that's so. Yeah, I was trying to think about what you are asking.
Right. Okay. Any other questions?
So it seems like there's some mathematical relation. There should be some mathematical relation between genus 1 and then these linear objects, which are these higher Grassmannians and so on. Do you know if there's some at least relation which seems like between these two things? Or
yeah, I mean no.
Sorry, this is a bit vague. I was just wondering if there's some already known kind of a connection between these two things.
I mean, I don't know of the connections in detail.
Okay, fine.
More questions? Okay, if not, let's thank Arnab again for a very clear talk.
Thank you very much.
Okay, bye everyone. See you next time.